Hi everybody, Mrs. Pesek here. We're looking at section 2.5, zeros of polynomial functions. Recall that an nth degree polynomial can have at most n real zeros. But in the complex number system, we can say that every nth degree polynomial function has exactly n zeros. So if we're talking about, a degree 4 polynomial function like f of x equaling 5x to the fourth minus 3x plus 1, that is guaranteed to have 4 zeros. They might not all be real. Some might be real, some might be imaginary, some may be repeated, but there will be 4. All right? So that brings up the fundamental theorem of algebra, which says if f of x is a polynomial of degree n, where n is greater than 0, then f, the function, has at least 1 zero in the complex number system. All right, so that's the fundamental theorem of algebra, but that's not, I don't think, as interesting as perhaps the linear factorization theorem that says if f of x is a polynomial of degree n, where n is greater than 0, then f has precisely n linear factors. Well, that goes along with the fact that if it's degree n, it's going to have n zeros, exactly n zeros. They might be real, they might be imaginary, they might be repeated, but there will be n zeros for a degree n polynomial function. So that means that corresponds to n factors, also n linear factors. Okay, so we could write a polynomial function as some constant a, and then times n of these factors, where it's x minus c, c sub 1, c sub 2, and so on, where those are each complex numbers. All right, let's take a look at some examples of finding these zeros. For this first example, we're finding the zero of f of x equaling x minus 4. Well, remember, what is the zero of a function? It means any number that makes our function equal to 0. So to solve for a zero of a function, you set your function equal to 0, and then you solve. So here we get that x must equal 4. That is the only zero of that function. And notice it was a degree 1 function, so it's got 1 0. Here's our next function. It's a quadratic. It's degree 2, so we're guaranteed to have 2 zeros. So we set this function equal to 0, and we solve the equation to find the zeros of the function. And this one actually does factor, doesn't it, into x minus 2 times x minus 2. And so we set each of those equal to 0, and we end up with 2 as a 0 twice. So these are the zeros of the function, and I would ask you to write them both. So 2 and 2. All right, let's try this one. We've got f of x equaling x cubed plus 9x. We're trying to find the zeros of the function. That means we want to know what x values are going to make our function equal to 0. So we set the function equal to 0. In this case, I think we could factor out an x. So we get x squared plus 9 times x. And then we're going to set each of these equal to 0. So I get x equals 0 or x squared plus 9 equals 0. So in this case, I can subtract 9 from both sides, and I get x squared equaling negative 9. And then I can take the square root of both sides here. Don't forget the plus or minus. And I get x equaling plus or minus square root of 9, which we can split up into square root of negative 1 times square root of positive 9. And that would leave us with x equaling plus or minus I times 3, or 3i and negative 3i. So if I'm going to list all my zeros for this example C here, my zeros would be 0, 3i, and negative 3i. I have 3 zeros, and it was a degree 3 polynomial function. 1 was real, 2 were imaginary. Let's take a look at letter D. We're trying to find the zeros here. I set my function equal to 0 to find the zeros. And in this case, I would not just add 16 and take the fourth root, because then you're only going to probably get maybe 2 zeros instead of all 4 that we need to find. Instead, maybe we could factor this. I see that this is a perfect square, this is a perfect square, and there is subtraction in between. So I could factor it into x squared minus 4 times x squared plus 4, right? And so if I do that, this actually factors further, because that's a perfect difference of two perfect squares again. So I get x minus 2 times x plus 2 for this one. And this one I can't really factor, so I'm going to leave it x squared plus 4. All right, so in this case, I'm going to set each of these equal to 0. And And so I get x equals 2, I get x equals negative 2, and here I get x squared plus 4 equals 0, so I'm going to subtract 4 from both sides. I get x squared equaling negative 4, and then I take the square root. Don't forget you need a plus or minus every time you take an even index of both sides of an equation. And so I get x equaling plus or minus 2i. So my zeros for this polynomial function would be 2, negative 2, 2i, and negative 2i. So this degree 4 polynomial function, where is it? Here's my degree 4 polynomial function, did have 4 zeros. 2 were real, and 2 were imaginary. Okay, that brings up the rational zero test. All right, it's a test that relates possible rational zeros of a polynomial to the leading coefficient and to the constant term of the polynomial. All right, now back in the day, before they had graphing calculators and they wanted to find zeros, they had to come up with some pretty elaborate tests to see what numbers might work to make a polynomial function equal to 0. So here's one of the tests. It's a rational zero test. And it goes like this. If the polynomial function f of x equaling a sub n x to the n plus a sub n minus 1 times x to the n minus 1 plus dot 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 all the way down to a sub 2 x squared plus a sub 1 x plus a sub 0 has integer coefficients, then every rational zero of this function is going to be of the form p over q, where the p values are the factors of our constant term, a sub 0. So our p-values are going to be factors of this. Okay? And then the q-values are going to be factors of our leading coefficient. So our q-values are going to be factors of that. All right? So, and hopefully you're not thrown by, this way of writing functions. We've talked about this before, that this is just a way to generalize writing a polynomial function. All right, so a lot of words here. Let's take a look at, I think I have an example for you. Yes, let's do this. Find the rational zeros of this function. Well, we're going to start by finding a list of the possible rational zeros. So we're going to list the possible rational zeros. If we make a list of possible rational zeros and we check them all with synthetic division and none of them work, then we can decide definitely that, or determine definitely that the polynomial function has no rational zeros. Because if there is going to be a rational zero, it's going to come from this list that we're about to make. Okay, so we need our list of p over q values to check. Okay, so in this case, remember we want p to be the factors of the constant term, so that's going to be the factors of 8, right, from here. And then we want to divide that by q, where q is going to be all the factors of our leading coefficient 1. Right, so here's our 8 here, and here's our 1 here. All right, so our factors of 8 would be 1, 2, 4, and 8, but don't forget we could have negatives of those. We need a plus or minus in front of each of those. And our factors of 1, well, that would just be plus or minus 1. So at this point, you need to find every combination of numerator over denominator. So that's going to be 1 over 1, 2 over 1, 4 over 1, 8 over 1, and so on. So our entire list here is just going to be plus or minus 1, plus or minus 2, plus or minus 4, and plus or minus 8. That's a total of 8 different possible rational zeros. So there are 8 different possible rational zeros. So that means if you did synthetic division 8 times with each one of these numbers and none of them work, then you could say, well, this polynomial has no rational zeros. All right, so at this point, we could start trying 1, then negative 1, then 2, then negative 2, and so on, but it might be easier just to test this with our graphing calculator. So we're going to plug in x cubed minus 5x squared plus 2x plus 8 into our graphing calculator and see where it crosses the x-axis. So let's do this. We're doing x to the third, x raised to the third and then minus 5x squared, and then plus 2x plus 8. All right, so this is the graph I'm getting. All right, so we want to kind of get a head start on this and say, you know, it looks like it's going through -1, for example, or it looks like it's going through 2, or it looks like it's going through 4. So let's just pick one of those values. Let's just try -1, and let's see if it actually works. So we're going to put -1. Actually, I could do menu, trace, graph trace, and actually type in a -1. Sure enough, it sure looks like it's a 0, but we're going to confirm that now with synthetic division. So we're going to put a -1 in the box, and we are going to put our coefficients, which are 1, -5, 2, and 8. And we're going to do our synthetic division. I'm going to bring down the 1, multiply, that's -1, add, that's -6, multiply, that's 6, I add, that's 8, multiply, that's -8, add, I do get 0. So it is confirmed that -1 is a 0 of this function. And that means I could write my function f of x as x plus 1 times x squared minus 6x plus 8. And then the x squared minus 6x plus 8 would factor further into, I believe, x minus 4x plus 2. Does that look right? No, that doesn't look right. Oh, x minus 4x minus 2. Does that look okay? I think that looks better. Okay, so, and then don't forget we still have the x plus 1. So remember, we can write this as it's a degree 3 polynomial function, and we said we could write it as a series of 3 linear factors. Well, there they are. Those are my 3 linear factors. And it's going to be guaranteed to have 3 zeros. I could set each of those equal to 0, and I would find out that my zeros are going to be -1, 4, and 2. Well, that is matched with what we saw on the graph. -1, 4, and 2, right? Those are all there. Okay. So let's take a look at another example. This time we want to find the rational zeros of 2x to the 4th minus 9x cubed and so on. Hang on, let me go back to this for just a second. I want to highlight something. Remember, we made that list of possible rational zeros here for that last example. This is my list of possible rational zeros, and I just want to point out that the 3 rational zeros that we found, -1, +4, and +2, were all in this list, right? -1, +4 was here, the +2, right? So they were all here. So the other ones didn't work, but that's okay. It was just a list of possible rational zeros. So let's make a list of possible rational zeros here. Possible rational zeros. And if we're going to make a list of possible rational zeros, that's going to be the p over q values. In this case, p is going to be factors of our constant term of -30. And then our q values are going to be factors of our leading coefficient of 2. So what are my factors of 30? What numbers go into 30? Well, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 5, plus or minus 6, plus or minus 10, and plus or minus 15, and plus or minus 30. Hopefully I didn't miss any. All right. So then we want to take a look at all the factors of 2, our leading coefficient, and so that's just going to be plus or minus 1 and plus or minus 2. So now you need to take every numerator over every denominator. So I want 1 over 1, 1 over 2, 2 over 1, 2 over 2, and so on. So let's make that list. So our total list of p over q's, these would be our possible rational zeros. Let me just list, I'm just going to take 1 over 1, 2 over 1, 3 over 1, and so on first. So I got 1 over 1, 2 over 1, 3 over 1, 5 over 1, 6 over 1, 10 over 1, 15 over 1, 30 over 1. Now let's take all of those over 2. So I need 1 over 2. So that means 1/2 and -1/2 are possible rational zeros. 2 over 2, but that's already 1, so I don't need to list that again. 3 over 2. All right, so plus or minus 3/2, those are possible rational zeros. 5 over 2, 6 over 2 is 3. I already have that in my list. 10 over 2 is 5. I already have that in my list. 15 over 2, I need to add that to my list. And 30 over 2 is 15. I already have that in my list. Now, this might look like a super long list, but it's only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 times 2 for the plus or minus. That's 24 different possible rational zeros. But here's the good news for the people that lived before graphing calculators. You would only have to try 24 times, and once you try 24 synthetic divisions, if none of them work, you can stop trying, because there won't be any rational zeros. All right. Luckily for us, we do have graphing calculators, so we are going to try this one on our graphing calculator. And so let's do that right now to see what the possible rational zeros would be. So I'm going to add a page here. Okay, so I am entering this polynomial function. It is 2x to the 4th minus 9x cubed. You're doing this with me, I hope. And then minus 18x squared plus 71x minus 30. Okay, so, I mean, I'm not seeing the full, I'd have to go up a little higher and lower to see actually where it's, you know, maybe I could do that. Just make this like, I don't know, make that like 100. Oh, that's overkill. Let's make this like maybe 25. Okay, so that's a little bit better, and maybe if I can change this down here, let me make that like a negative 20. Nope, that needs to be going down lower. Let's see, how about negative 45? Okay, well, you get the idea that it's curving like this, and we're seeing where it's crossing. Looks like it's crossing here, here. It looks like it's crossing 4 places, and it is a degree 4, so it sounds like we do have 4 real zeros, not imaginary. And so I would just say, well, let's try this one. Looks like it's going right through maybe negative 3. So you could test this with menu, trace, graph trace, type in a negative 3. Sure looks like it's a 0. So let's go ahead and do synthetic division with this, because we're trying to find out whether this works. So if I try negative 3.
Ma'am, Myers, please come to the office.
So we're going to try negative 3. In the box, I got 2, negative 9, negative 18, 71, negative 30. And so let's try this and see if we get a 0 for remainder. I bring down the 2, I multiply, I get a negative 6. I add, I get a negative 15. I think that's going to be a 45. What's 45 minus 18? Is that a 27? I think. I'm going to go with that. And then negative 3 times 27 is negative 81. That's going to be a negative 10. When I add, that's going to be a positive 30, and I do get a 0. So that works to give me a 0. And now if I want to find other zeros, I might try another number that it crosses at, maybe 2. It looks like maybe it crosses at 2. So I could try that. Put 2 in the box and use these numbers now. And I have 2, negative 15, 27, negative 10. And if I try this, hopefully this is going to work. I multiply, I get 4, negative 11, negative 22, that's a 5, that's a 10, that is a 0. So what did I learn so far? I learned that negative 3 works in the box, which means x plus 3 is a factor. I learned that 2 works in the box, so x minus 2 is a factor. And that would leave my last factor as 2x squared minus 11x plus 5. And I bet this factors further. If we do product sum, it might factor. Product is 10, sum is negative 11. So the 2 numbers that would work would be negative 10 and a negative 1. And so I can write this as 2x squared minus 10x minus 1x plus 5, factor by grouping, and I get a 2x times x minus 5 and a minus 1 times x minus 5. So I get 2x minus 1 times x minus 5, and don't forget, I still have these, x plus 3 and an x minus 2. So if I want to find all my rational zeros, I would set each of these equal to 0, because this is my polynomial function now in factored form as a series of 4 linear factors. And I would get -3, +2, 1/2, and 5. And I think that would all be matched up with what you would see on the graph. All right. Okay, so that's it for that example. We found all the zeros, the rational zeros. This one says find all real solutions of this polynomial function. So again, we would start off by listing our P over Q values. The P over Q values would be plus or minus, let's see, we need our factors of 14, so plus or minus 1, plus or minus 2, plus or minus 7, plus or minus 14, over our factors of our leading coefficient, which is 1, so that's just over plus or minus 1. So my possible rational zeros would just be 1, 2, 7, and 14, and the negatives of those. So again, I would graph this on a calculator, all right, to see what the graph looks like. This is, we're going to type in x cubed minus 7x squared minus 11x plus 14. So let's do that. I'm going to my calculator, adding a graphs page, and I'm typing in x cubed minus 7x squared minus 11x and plus 14. All right. Well, that was bad. Okay, let's not do that. Let's, oopsie. Yeah, I didn't like that at all. Let's add another page. Get rid of that one. So I did not do a right click after I did my x cubed. Okay, so now I need to do a right click. Let's try it again. Minus 7x squared. That was an interesting graph, though. Minus 7x squared minus 11x, and then plus 14. That looks a little bit better. So remember, we made our list. I don't know what this one is. It looks like it's going somewhere between 0 and 1, but it sure looks like it's maybe crossing at -2. Let's test that with menu, trace, graph, trace, type in a -2. That sure looks like a winner. So let's go back here and try -2 in synthetic division. And I'm going to put in 1, -7, -11, 14. So I bring down the 1, I multiply, I get -2, that's going to be -9. I'm going to get a positive 18 here. I add and I get 7. I multiply and I get a -14, which is 0. Okay, that leaves me with my function f of x could be written then as x plus 2 as a factor times x squared minus 9x plus 7. All right, does this factor, the product would be 7, the sum would be -9, not looking good. So I don't think it's factorable. So guess what we have to do to find the remaining zeros? Because the directions say find all real zeros. So they might be irrational instead of rational. So we need to do quadratic formula. So we're going to use quadratic formula on this problem. And we're going to plug in these numbers. So we're going to have opposite of -9 is +9 plus or minus -9 squared minus 4 times 1 times 7 over 2 times 1. And we end up getting 9 plus or minus square root of 81 minus 28 over 2. And you can see we're going to be getting some irrational zeros for this. So 81 minus 28 is 53. So I get 9 plus or minus square root of 53 over 2. So my zeros for this, I'm asked to find all zeros. -2 would be one of the zeros. We saw that with the synthetic division. And then 9 plus square root of 53 over 2 would be another 0. And 9 minus square root of 53 over 2 would be the third 0. So 3, you're guaranteed to have 3 zeros. Okay, we're going to stop here for this lesson, and thank you for watching.